Imagine standing beneath the blazing sun and hearing it roar. Strange as it sounds, recent data suggest our star is actually getting louder in the realm of heliosysmology, and nobody's quite sure what's behind it. Underneath the solar surface, the churning of hot plasma creates pressure waves, essentially sound waves, that bounce around the sun's interior, setting it vibrating in millions of patterns called P modes. These oscillations have frequencies around 3 to 5 MHz, periods of roughly 5 minutes, and are detected by measuring tiny Doppler shifts in sunlight using instruments like SOHO's Michelson Doppler Imager or NASA Heliosysmic and Magnetic Imager. Until recently, these acoustic signals maintained a fairly steady amplitude, acting like a clockwork metronome of the sun's heartbeat. But now, helioseismologists are reporting a steady and puzzling rise in the amplitude of certain P modes over the past decade. In other words, the sun's interior bell is ringing louder than ever before. A groundbreaking study in Nature Communications used heliosysmic techniques to probe solar radiative opacity in the sun's deep layers and found discrepancies between observed wave behavior and theoretical models. Those tiny mismatches in how radiation is absorbed could be hinting at a shift in the sun's internal structure, enough to tweak the way acoustic waves are generated or damped, and thus turn up the volume on our star's symphony. You might be thinking, cool science. But so what? Here's why this mysterious, louder sun could matter to all of us. Space weather forecasting. Heliosysmology isn't just academic. Scientists rely on these oscillations to map flows of plasma and magnetic fields beneath the surface. A change in wave behavior could signal shifts in the solar dynamo that drive sunspots, flares, and coronal mass ejections. That, in turn, might make solar storms more unpredictable, jeopardizing satellites, power grids, and astronauts. Climate connections. The sun's acoustic oscillations subtly reflect variations in its energy output. If the amplitude shifts tie back to changes in heat transport within the sun, there's a chance, still highly speculative, that solar irradiance could vary in unexpected ways, influencing Earth's upper atmosphere and, over long timescales, climate patterns. Fundamental physics. The sun acts as a natural laboratory for extreme physics. Any new anomaly in P-mode behavior forces us to refine models of plasma, atomic interactions, and even neutrino production in the core. Unlocking the cause behind the louder sun could reveal gaps in our understanding of stellar physics that ripple out to how we model other stars and exoplanet systems. Right now, teams at NASA, ESA, and institutions worldwide are combing through heliosysmic archives to confirm whether the amplitude rise is steady, cyclical, or tied to the 11-year solar cycle. They're also developing new instruments with higher sensitivity, hoping to catch subtle shifts in wave frequencies and patterns. In parallel, theorists are tweaking stellar models, adjusting opacities, magnetic field configurations, and even exploring exotic physics like dark matter interactions in the core to see what could produce a bump in acoustic power. So yes, the sun may indeed be getting louder, but remember, you won't hear it in the traditional sense. These subsonic waves remain hidden beneath the blaze of light, revealed only through clever science and patient listening.